the tank level increase, what's going to happen to the flow out?
More pressure and more.
The pressure will get it to, right? Because the flow out is proportional to the head pressure of the tank, right? So the process will be stable without any feedback control, without any. You understand that, okay? So that's number one. That's chapter one, by the way. If you look at all that in chapter one. Now, manual control. We know that we can do manual control. Someone monitor the process variable, someone activate the valve and all that. What is the purpose of automation?
They don't have to have it.
So you don't have to do it yourself.
No, that's not the main reason. No, because no, that's not the main reason, by the way.
More accurate.
Exactly. You have to have the same product all the time, otherwise you lose your customer. By manual operation, no one can do that.
Right.
Like, if I want to market my baklava for franchise,
Yeah.
I cannot cook it myself. I have
Right.
to automate the process. Why? Because I want it to come exactly the same, otherwise. So that's the reason why we have control of automation. Now, we started here to talk about automatic control, and we talked about, now, sensor, if you remember, what did we study about displacement sensor? Anyone can remember that?
Displacement.
Yeah. Anyone remember? Level? LVDT? You
Yeah.
remember that when we talked about the capacitor? We'll come to it, but it's okay. Here, only the activator, you have to understand what's the definition for the activator. Activator switch the control signal into an action to activate on the valve. So you can look at your activator here as the motor will drive the valve. You have to know what's the definition of the actuator. Receive the signal from the controller and switch it to an action to act on the controller. Now, block diagram of control loop. We talked about it many times. What it has, controller, read here, controller, control element, final control element could include the activator to act on the final control element, the process itself like heating, temperature, tank level, and then we have the measurement, and then we get there. So the basic element in the process is whatever you see here. The controller, the control element, the process, the measurement. Okay? Block diagram of control loop. The processor error signal in the controller is obtained by subtracting the measured variable from the set point. We know that. Error is getting, and we know that we have positive error or negative error based on that's bigger or that's bigger, right? Okay, here, what do we have? We have physical diagram of the control loop. What we trying to do if you look at that? Tell me quickly. What are we trying to
Pressure.
do? What the controller trying to do?
Pressure converts to current.
We have pressure to current, right, transducer, and we have current to pressure transducer. And all what we're trying to do is we're trying to control the flow inside this part. By measuring the flow, feed it to the controller, and we have target for the flow rate, right? And then the controller, whatever it is, PID, PI, PEG, will decide on the output, and then the rest transducer will switch from current to pressure if that's what's activating the valve to control the flow. So all of that was in chapter 1. Chapter 2, we talked about analog signal. Voltage divider, we used it for what? To vary the resistance. And we are very good about that. Remember the Wheatstone bridge? When we had the RTG, the sensor, to sense the temperature, and it gave us variation in the resistance, and we were able to switch that to signal, and then we feed it to analog input module, which is A to G. So VG equal this voltage times R2 divided by R1 plus R2, and if R1 equal R2, and we have 10 volt here, we have 5 here and 5 here, and we know how to do with that. Okay? The basic DC Wheatstone bridge. We said if the bridge in balance, it means that VA equal VB, and the voltage across is 0, and right away R1 times R4 equal R2 times R3. You remember all of that, right? And we used it for temperature, as temperature detector, and we switch it to analog signal. Now, R Thevenins and V Thevenins. Here, what's V Thevenins? Let's start by R Thevenins. What's R Thevenins? Between A and B, you remove the galvanometer here, and you're looking at this circuit from those 2 points, and you short the voltage. And what did we say about R Thevenins? When you short the voltage, and you open the galvanometer, and you look between A and B, R1 will be in parallel with R3, R2 will be in parallel with R4, and the R Thevenins will be here cluster, right? Okay, how do we get V Thevenins? We open the galvanometer and we look between A and B, and V Thevenins equal VA minus VB. What's VA? V times R3 divided by R1 plus R3. What's VB? V times R4 divided by R2 plus R4, and we get the V Thevenins. So we can analyze the circuits, and we put the galvanometer back, we put the resistance, and we can get the current or whatever. We did all of that, if you remember, right? Okay. We didn't do much about AC, but it works the same thing as DC. Z1 times Z4 equals Z2 times Z3 under balance, and it doesn't make any difference. Then we started to talk about a circuit for low pass filter. What did we say about the low pass filter? It tests the low frequency and it blocks the high frequency. And we looked at ZC. What's ZC? 1 over J omega C. So at low frequency, omega is equal to pi f, which is going to be 1 over 0, infinity, and we'll test the whole. Right? And what is the cutoff frequency? 1 over 2 pi RC. You have to know all of that. Okay? And from the curve here, we got the magnitude of V output over V input versus the frequency of the signal over the cutoff frequency. I was talking about it. And you look at here, it tests all the low frequency and it drops the high frequency. Same thing will happen for the high pass filter. We'll test the high and we'll block the low frequency, and it has the high frequency, and same thing. Then we started to talk about the op-amp. We defined the op-amp as a high input impedance, low output impedance, and we used it in instrumentation as a differential amplifier, and we designed the the conditioning signal, and we did all of that. Also, we can use it to sum, we can use it to compare, we can use it to differentiate, we can use it to integrate, but we use it as a signal condition. We started by V output over V input equal negative R2 over R1, while R2 over R1 is the gain. So if you make R1 equal R2, V output equal what?
Input.
Negative V. So you can invert the signal. That's why it's called inverting op-amp. If I make the R1 equal R2, I have gain of 1, and V output over V output will be negative. And we did that with some of these. Then we started by the op-amp as a voltage flower, and we said it has very high input impedance. We were able to isolate, and we started to design the signal condition. You remember where we used that? Anyone? In one of the labs. What is it? Yeah, we used the op-amp as a summing amplifier to do what?
Digital to analog.
Very good. Digital to analog converter, and we used weighted value of the resistors. 1/8, 1/4, 1/, and so on, right? And that's how we use that one. So V output here, you know, it's equal negative V1 R2 over R1 and so. Tell me if you don't understand anything. Now, this here, the gain here should be greater than 1, right? The non-inverting amplifier, the gain of non-inverting amplifier is always greater than. You know that, right? All this definition you have to know about it. And we used it in one of the lab, if you remember, the signal condition we did. Then we started to use the basic differential amplifier configuration also in signal conditioning before we go from the signal to the A to G converter. And V output is equal R2 over R1 times V2 minus V1. If you remember, we did the equation and we took common factor. You remember all of them? And we worked homework problem. All of that is very important to review and to work with it. And instrumentation amplifier includes voltage floor for input isolation. We did that also before. Signal conditioning that provides 0 to 5 volt from a sensor output 20 to 250 millivolts. If you remember, the output was going from 0.2 volt to 0.25 volts, and the input from 0 to 5, and we got Y equal mx plus b, and then we had to take common factor. Finally, we put this equation, and the gain here is 2.17, which is 200. You remember this problem? Yeah, expect to do all of that in the final. If you don't remember, tell me. So what that here? The 0.02 volt.
2 volts. Voltage divider.
Remember the equation was V output equal R2 over R1, V2 minus V1. That's V2 minus V1. So V2 was the signal coming to us, and V1 was fixed, which is the constant. You remember all of that? Okay. So that's the solution of that one. Chapter 3, we started to talk about the elements of final control element. So we started now to talk about the control signal going from D to A. Here we're going to start going digital to analog converter. So when we go digital to analog converter, we're going to send the signal to the actuator, then we're going to send it to the final control element, then we're going to start. So you have to know all this definition. What does mean actuator? Take the signal from the controller, switch it to action to activate on the final control element, and then changing the process. All of that you have to know. Then we started the, remember when we started to talk about digital, we talked about the control as on-off, control to mode control. And when we started to talk about that, we started to talk about hysteresis. What does it mean? That we never send output to the final control element on-off, on-off. We work with pressure. It's called in the digital Schmidt pressure. Below certain level, it's off. Above certain level, it's on. And in between, it's latching from where you came from. So if the error is less than 0, you turn off. If the error is greater than 0, you turn on. And we call it on-off control versus continuous control of the LTO. We started to talk about some Boolean equation, but we didn't do much. You are very good about that. You have no problem, right? You are okay. So what's the output here?
What's the output?
What is the output here?
D.
What is D?
D is, let's see.
No way. What is D?
D is.
The output. Is that or that? Right?
Yeah.
Either or.
Right. So D is equal this expression plus this expression, and then you can work with minimization and you can do